Thank you so much for the introduction and inviting me to give a talk. I really love this seminar series, and it's very great for the development of the knowledge in this area. So this paper is based on the same titled one published this year and Annal of Applied Probability. For more information after this talk, you can refer to that paper. The random walk Metropolis (RWM) algorithm, in short, is the most classical MCMC algorithm, has had a great influence on the development and practice of science and engineering. Most practical MCMC algorithms can be interpreted as special cases or extensions of the RWM algorithm. The behavior of the RWM in high-dimensional problems is typically investigated through a weak convergence result of diffusions. In this talk, I will talk about the Mosco convergence of Dirichlet forms in analyzing the RWM algorithm on graphs, whose target distribution is the Gibbs measure that includes any probability measure satisfying a Markov property. So let's firstly warm up on what is the Metropolis Hastings algorithm. Initially, we generated the initial state x, 0, n. N is the index for dimension. According to pi n, that's the target distribution. It's the n-dimensional. And we set t equals 0. That's the first step. Then next, we iterate to the next step by generating each of the R1 to Rn from a symmetric distribution, PDF, phi. Next, we generate a random candidate state, Yn equal to xnt plus sigma n R1 to Rn. Then we calculate the acceptance probability. An is a function of the xnt and yn in the form of mean function 1 and phi n yn divided by phi n x and t. Then after that, we accept or reject by generating a uniform random number u in the range 0 to 1. If this u is less than or equal to the an function, then we set xn t plus 1. That's the next step's value as yn. Otherwise, we set the next value as xn. Then we go to the next step. Okay, so this is a very standard setup of the Metropolis Hastings algorithm, also the very basic one. There's more fancy ones. Now we talk about what is the Gibbs measure. Gibbs measure is the generalization of the canonical ensemble to infinite systems, where a canonical ensemble is a statistical ensemble that represents the possible states of a mechanical system. The statistical ensemble gives the probability of the system X being state little x as this form. It's 1 over c. C here is the normalization constant, also being known as partition function in statistical physics. And the exponential negative hx. Hx here is the Hamiltonian function, also being known as energy function. Mu is the reference measure. For the finite systems, Gibbs measure, Gibbs distribution, or Boltzmann distribution are used interchangeably, whereas one can only use the terminology Gibbs measure for infinite systems. The Hemsley-Clifford theorem implies that any probability measure that satisfies a Markov property is a Gibbs measure for an appropriate choice of locally defined energy function. Here we consider the Gibbs random field on a general graph G that is combined by V as the set of vertices and E as the set of edge. The countable set V is considered to be located on the d-dimensional Euclidean space Rd. G can be a finite graph such that the cardinality of the vertex set is finite, or an infinite graph such that the cardinality of the vertex set is infinite. Now we can see two examples. The left one is the 3D lattice, And on the right is a 3D graph. Each vertex k in the set V is given a real-valued random variable we denote as xk. Although the Gibbs measure was proposed to provide a framework to directly study infinite systems, the energy function may not be finite in infinite systems. Hence, the Gibbs measure is defined in terms of the conditional probability that it induces on each finite subsystem. We consider Vn as an exhausting sequence of subsets such that Vn goes to V as n goes to infinite. And we denote X subscript Vn. So this is a standard notation for the random field terminology. This is xk for the key in the index Vn. We call it a configuration on Vn. So this is the name of that configuration. The Gibbs measure focuses on the Hamiltonian HW. W is a set. It's a finite subsystem in this V, set of vertices. So HW has two arguments, ZWC. So this means conditional on the value of WC. C stands for the complement of this W set. And then the SW. So this is the conditional distribution on some fixed boundary configuration ZWC. So the definition of this is pi W z dx given by 1 over zw. So the normalization constant is based on W. And the exponential negative Hamiltonian function also based on W. Then ZWC, XW. And then the reference measure is on XW. So this here we have the product topology here. Being this, we consider the Lebesgue measure of the reference measure because this is already a finite system. And we also assume this Hamiltonian is in the form negative summation k in this W, hk, ZWC, XW. So this is the form. So we can see here is above is negative capital H, and then the capital H is another negative. So it's negative, negative. So the function is on little hk later. Then the Gibbs measure is defined as a family. This capital pi is a family of little pi W. Okay, so this is a family of conditional probabilities on the finite system. This kind of family satisfies the following consistency condition. This set is the integral pi W times the pi U is pi W. So this is the form actually consistent with our Tor property of the conditional expectation. The optimal scaling problem of the RWM algorithm is a high-dimensional implementation problem, considering the case that the dimension of the target distribution, little n, goes to infinite. It investigates this sigma n. Okay, so now let me show you where is this sigma n. Sigma n is here in the algorithm. So we consider about this sigma n. Okay. It investigates sigma n, which is the variance of the random walk step, aiming to answer two questions. First, how should the sigma n scale as a function of n so as to optimize the speed of convergence of the algorithm in the limit? Second, is it possible to categorize optimality of sigma n in a way that can be practically utilized? It turned out, in the classical work by Gelman, Gilk, and Roberts in the year 1997, it is optimal to scale the variance of the proposal as big O n inverse. Okay. So now let's talk about another classical result. This classical result is considering this graphical setting, but the previous one is just the first result. One of the first results. So now let's take a look at the key result using the diffusion approach. Firstly, as n go to infinite, the expected acceptance rate of the algorithm is converged to C is a function of tau. Tau is here. This is constant tau. Where for n is a standard normal random variable, this C tau can be expressed as this way. Okay. One that exponential negative tau s function defined here, with this n standard normal minus 1/2 tau square s square. Okay. We are going to work more on this s pi later with a practical example. The key result number 2 in the topology of local conference xn, this is the time reskewed. This is the integer part of the index t times n. This is weak convergence to zt, almost through everywhere with pi. Where this z is the infinite dimensional large Venn diffusion, solving this as a stochastic differential equation. This is the infinite dimensional. Zt equal to z0 plus integral tau square root of c tau EBS. This is the standard Brownian motion. And 1/2 the integral 0 to t tau square c tau. This is gradient of the Hamiltonian function, then ds. Okay. Thanks to the standard normal random variable n in this form of the c tau, we can write c tau in another way. This is 2 phi, capital phi, negative 1/2 tau s pi. This phi is the CDF of the standard normal. Then based on that, we can solve the tau star. This is the argmax. This is the optimizer of this tau square CT. Okay. And this is actually equal to the argmax 2 phi. Just plug in this form. And this we can approximately solve this at 2.38 divided by the s pi. Therefore, the C tau star can be solved as 0.234. So this is a very classical result in this optimal scaling literature. That means the maximizing value of expected acceptance rate of the algorithm is approximately 0.234. So now let's take a look at the hypothesis in the diffusion approach. H1 is, so let V, okay, curly V is a finite subset of ZD. They consider the graphical structure as ZD lattice, such that 0 is in this set. And for any set V in this curly V implies another negative V also in this set. So you can see this set is quite symmetric. For each k in ZD, we consider the HK. HK is a function of the finite set V, curly V, plus k. That's where this k comes from. Goes to R. This is the C3, the third order derivative continuous. And such that HK, if you change the position of that, you get the same function. Okay. This is the transition invariant. We assume that the family of Gibbs measure in this form, where this pi w, as we just explained, is tight in the local topology. And for the pi, this family in the G pi is a non-empty set of translation invariant Gibbs distribution. So that's our assumption on the function, the Hamiltonian function, and the graph structure. Okay, that's their assumption by the diffusion approach. Later, I'm going to relax that. And H2 said the family, the pi n is based on the Vn. This is an exhausting sequence of the vertex set. This set is satisfied the condition the vertex number is little n, and the sup V prime n is the convex hull of this Vn. The vertex number divided by Vn's is finite as n, and also as n go to infinite, the supremum of the radius, the sphere entirely contained in Vn go to infinite. Next, they assume the boundary condition of the graphical set. This V plus the boundary of Vn divided by the cardinality of Vn is bounded by C is a constant and n with the power of negative alpha. Okay. Furthermore, they assumed the H3 set for every n in ZD. The second order, third order derivatives of the Hm are bounded. H4. The Gibbs measure satisfies for some delta bigger than 1. There is some moment conditions. 2 delta. H5 is for each k. The function hk satisfies the Lipschitz and Gross conditions as below with the Euclidean norm. Now there comes the complicated H6. Okay. As we can see, the form with this one is actually about the defined strong mixing coefficient of the set probabilities and also the some distance, set distance involved. Okay. Clearly, this assumption is quite complicated. Luckily, with the Dirichlet form approach, we don't need this assumption H6. To be honest, actually, no example satisfy the H6 were provided in the classical work by the Breer and Roberts. Also, due to its complexity, verifying instance poses a significant challenge, and as a result, we are unable to locate any of the example or counterexample of H6. Further lucky, the H4 and the H5 can be removed by our Dirichlet form approach. A counterexample is why this removing these conditions is important. Let's say one counterexample. The generalized normal distribution, also known as exponential power distribution, is a family of continuous probability distributions that generalize the normal distribution by introducing an additional shape parameter, beta, which controls the kurtosis, that's the tailedness of the distribution. The PDF of a generalized normal distribution is given by this form, f with 3 parameters, mu, alpha, and beta. So mu here is a location parameter, alpha is a scale parameter, and beta is a shape parameter, and there's a gamma function. The shape parameter here controls the tail behavior when beta equal to 2. This form is exactly the normal distribution, but it cannot equal to 2. Say, when beta bigger than 2, the tail of the distribution is lighter than those of the normal distribution. The first order derivative of the log density is given by this form. Here, there is a sign function, okay, which takes the value 1 if the x bigger than mu, and -1 if x is less than mu. When x equal to mu, that is 0. When beta is bigger than 2, in this case, you can see there are many values. When beta is bigger than 2, this density, the log density, the derivative z does not meet the growth condition required by the H5. Okay, so that's one counterexample. Later, we are going to use this example to numerically illustrate the optimal scaling result. Now let's take a look at the assumptions by the Dirichlet form approach. So let's first record in the H3. They considered is lattice, and then I consider it is a general vertex set. And they assume the second order and the third order derivative as bounded, but I only need the second order derivatives of Hm are bounded. Okay. And the other counterexamples not satisfying the third order derivative boundedness is provided in my paper. Now after we talked about the regularity assumptions of the distribution function, now let's take a look at the graph generalization I can achieve. They assumed the V is to be a finite subset of ZD, and I consider this as a finite additive subset of V in the graph distance. Okay. Next, they assume the HK to be C3. I don't need that, but I do need its translation invariance. Probably this condition can be further relaxed if you consider further general graph structure, but in this paper, we focus on the comparison of the convergence approach, not just this generalization of the graph is not our main focus. Okay. So now let's observe the illustration of the generalized additive property. The left figure depicts of the typical lattice structure, while the right figure is from Ho in the paper published in Scientific Reports in the year 2015. This showcases a distorted lattice structure in the real scientific application. In the real life, lattice is still some kind of restricted. We can always relax that somehow. So now let's talk about the Dirichlet form approach. The abstract and powerful theory of Dirichlet form, and specifically the notion of Mosco convergence, allows us to work directly and naturally on the infinite dimensional space. With the diffusion approach, Breyer and Roberts was only able to prove the existence of the limiting diffusion on the state space, L2 space, which should be RZD. In fact, the infinite dimensional space RZD is not a Banach space because its topology cannot be derived from any norm. That is, with the diffusion approach, they have to reduce the state space from one that is not even a Banach space to a Hilbert space. That embarrassment is naturally avoided with the Dirichlet form approach. So our Dirichlet form approach works on changing Hilbert space. This Hn is L2 based on RVn and then pi n to H L2 RV pi. The definition of the changing Hilbert space is given below. A sequence of the Hilbert spaces Hn converge to Hilbert space H if there exists a dense subspace C in H, and a sequence of operators gamma n from C to Hn with the following property. The limit n go to infinite of the Hn norm of the gamma nf is equal to the H norm of f for every f in C. Here, this gamma n operator is asymptotically close to a unit operator. However, it's not necessarily injective even for sufficiently large n. And for the NF and GEH, we have to also clearly define the inner product and the associated norm. Also, we use that a lot in the paper. Denote the Euro L2 inner product. Fh, that's the integral fx, gx, and then pi x. And the related norm is the h norm of f is just the inner product of ff under h. Now we are ready to give the definition of the symmetric bilinear form. For a function e, this is from the domain dE and dE to R, where the domain dE is some subspace of the H. We see that it's a symmetric bilinear form over R if the following three conditions hold. Firstly, EUV is equal to EVU. We can exchange the position of the argument. Next, this is a multiplicative property. E lambda u, lambda is a constant, is equal to lambda EU. The third one is additive property. EU plus V W, that's equal to E UW plus E VW. So next, we see that a symmetric bilinear form E is a symmetric Dirichlet form if the following three conditions hold for any of the UV in DE. Firstly, E is a non-negative definite. So EU is equal to, this is a short abbreviation for EUU, is a non-negative. Next, E is closed on H. That means the domain of E is complete with respect to the norm of E1 half. Here, this E1 UV, this norm is defined as EUV plus UVH. The third one is one has U star is inf of sup UV and 1. This is in DE and EU star less than equal to EU. So this is the definition for the symmetric Dirichlet form. And there is a non-symmetric Dirichlet forms. That's a generalized version of that. We can find this in the Ning Ning and I forgot the co-author's name. There is a classical book on the non-symmetric Dirichlet forms. If you are interested, you can refer to that classical book. The first author's name is Ning Ning. The Dirichlet form En on the Hn, which associated with the n-dimensional time scaled Rwm chain Xn, the integer of the Tn, is in this form. ENU equal to n over 2 expectation of u, that's the first step's value, minus u, the current the 0 steps value, for any of the u in the domain, such that the ENF less than infinite. Next, we also need the generalization to the infinite space. Okay. So, to the Hn space. So we commit a slight abuse of notation by identifying this En on this Hn. By simply, if U in this domain, we set as ENU. Otherwise, if it's not in this DEN, we set just as infinite. That's a generalization to Hn. This lemma is very important. Basically, any of the optimal scaling results, either using the diffusion approach or any other approach, we need to firstly analyze the acceptance function. And this is a very important result here. That's the expectation of the acceptance function converge to this C tau. And the C tau is in this form. And we also need to achieve this result in this graphical setting. Okay, so now let's analyze the infinite dimensional Dirichlet form. That's the limiting situation corresponding to the limiting the infinite dimensional large Venn diffusion. So we have the infinite dimensional Dirichlet form. So although the infinite dimensional space RV is not a Banach space as we just explained because its topology cannot be derived from any norm, it's a locally convex Polish space. Polish space is a locally convex with a completely metrizable space with respect to the product topology because its weight is countable. We can define a linear space of functions on this RV by this curly f CB infinite. This is a function of a finite argument, x1 to xm. And this function f is CB infinite Rm. This set of the family of functions denotes the set of all infinitely differentiable real-valued functions on Rm. It's a finite dimensional argument with bounded partial derivatives. By the Hahn-Banach theorem, this family of functions separate the points of RV. RV is a Polish space. Then this family of functions is dense in L2 RV pi by the monotone class argument. So now we are ready to define the Dirichlet form. But we first need to define the partial derivatives. Okay, so we have the partial u over partial k, z. This is defined as z is d over ds over the u z sek under the s equals 0. That's how we define that for the infinite dimensional situation. And ek is the delta kg. delta here is the Kronecker delta. And we define the partial Dirichlet form as this form. This is the EKU, tau square C tau over 2. Integral of this partial derivative taking square d pi. And then this EKF, this function, family of functions we just defined here, is a positive definite symmetric bilinear form on H. Next, EK and its domain is a closed extension of the EKF CB infinite. Okay. And now, can we define the infinite dimensional Dirichlet form yet? Okay. So next is we record the V is countable. We can define the linear space. That is, we take the intersection of the DEK. Okay, EK is here. This is a partial Dirichlet form. And according to this kind of setup. And after that, we simply combine this together. It's a summation of the K in V and the partial Dirichlet form. Eventually, the infinite dimensional Dirichlet form is given in this form. Tau square C tau over 2. The integral of the square of the gradient of U, taking square d pi. And as before, we extend that to the infinite dimensional space. Okay, so now after that, the rigorous setup of Dirichlet forms from the finite dimensional to the infinite dimensional are all set. Then we are ready to analyze based on the Mosco convergence. The definition of the Mosco convergence was originally due to Mosco in the year 1994 for a fixed Hilbert space, CH. Later, Covey and Shioya in 2003, about 10 years later, extend it to the changing Hilbert space as below. We see that a sequence of bilinear forms En converge to the bilinear form E if the following conditions hold. M1 condition if the sequence Fn for F in Fn converges to F weakly, then EF less than equal to lim nth n, go to infinite, En Fn. M2, for every F in H, there exists a sequence Fn where Fn in Hn. Converging to F strongly such that the EF equal to the limit of En, Fn. You can see here not just the En changing, also the argument Fn changing. So there are two theorems under the assumption imposed. The sequence of Dirichlet forms En Mosco converges to the Dirichlet form E. This assumptions is we illustrated earlier. And next, if we define the semigroup Tn as here, that's the standard setup for the semigroup in stochastic process setting. This is given by the Ex, it's the expectation under X, U, X, N, T. Let Tn be the semigroup of En and T be the semigroup of E. So the Mosco convergence of En to E is equivalent to the strong convergence of Tn goes to T for every T. And now let's compare the Dirichlet form approach and the diffusion approach. If we associate the Dirichlet form E with the non-negative self-adjoint operator negative A, such that the domain of square root negative A is equal to the domain of E, and we set this E, the Dirichlet form UV equal to negative AU, this is the adjoint operator A, negative AU, V. For the UV in DE, A is called the infinitesimal generator of the semigroup of ATT, satisfying the following equation. So this equation is the infinitesimal generator of the self-joint operator in the diffusion setting. This corresponding to the infinitesimal generator of Z, as we mentioned earlier, of the infinite dimensional large event diffusion, is given by here. So from that, we can see this Dirichlet form in the infinite dimensional case is exactly the same as the infinite dimensional large vane diffusion. It's the same thing. Okay. So now I'm going to skip the proof strategy due to the time constraint, but I want to acknowledge that I'm not the first work of the Moscow convergence of Dirichlet forms in optimal scaling problem for RWM. The first work was introduced in the year 2017 by Zanila, Bedard, and Kendall. It's a very great, very beautiful work, but they worked on the RID product form target density, and they used the original version of the Moscow convergence. In order to use the Moscow convergence, in that version, they did not consider the changing Hilbert space. They embed everything on the infinite dimensional space. That's the first version of Moscow convergence. And in order to use that, they embedded the finite n-dimensional Markov chain into the infinite dimensional space R infinite, and updating the first n component while drawing the remaining component independently from the target distribution, and then holding fixed. So they consider it as product form target density, and I consider it graph-based, and there is a non-product form target density. There is a dependence in that. Okay. So with the RD product form target density extending to the extending a finite dimensional chain to the infinite dimensional chain is not necessary. In fact, it can be tackled by sampling a single one-dimensional target thanks to the product structure. This is by another very excellent work by Yang, Roberts, and Rosenthal in the year 2020. Okay. And then the probability distribution may not be finite in the infinite dimensional case, such as the Gibbs measure. Therefore, I introduced the general formed Moscow convergence for the dependent target distributions. Okay, so I'm going to skip the proof strategy and move directly to the illustration of this approach numerically. The family of generalized normal distribution has gathered significant attention from the engineering community due to the flexibility of its parametric form in modeling various physical phenomena. In this section, we focus on the generalized normal distribution, which has the following PDF. You can see there are 3 parameters. In this numerical illustration, we set mu equal 0, alpha equal to 1, and beta equal to 3. As we recall, when beta equal to 2, that's the normal distribution. This PDF does not satisfy the growth conditions specified the hypothesis H5 in Breer and Roberts. However, we have relaxed this requirement by utilizing the convergence of Dirichlet forms. The Python code that reproduces our numerical result is publicly available on GitHub. Actually, I believe this is another contribution of this paper, because most of the optimal scaling papers are highly theoretical, and I did not aware any straightforward code released or publicly available. It's quite understandable, because this work is usually quite theoretical. Theory proof is the focus. But in this paper, I provided the reproducible Python code, then people can practice on that and play with it. Okay. So next, we think about the acceptance rate versus the proposal scale for 4 Markov chains. Each curve represents a different chain, and the horizontal line endpoint 234 marks the optimal acceptance rate for the RWM algorithm. Okay, so we can see, and that is the one. That's acceptance rate and the proposal scale. And 4 independent MCMC chains were generated, each starting from a 100-dimensional zero vector. For each chain, we run 20,000 iterations of the RWM, discarding the first 5,000 samples at the burn-in period to ensure that the chain was not influenced by the starting point. The proposed distribution used was a multivariate normal distribution centered at the current state with the variance-covariance matrix being the identity matrix. 5 proposal scales 0.3666, 1.366, 2.366, and then 3.366, 4.366 were tested. Well, the second one is calculated by the formula. So this is matching the theoretical result tau star 2.38 over S pi. And in this example, S pi is derived by this formula. Okay. That also we use the moment result for the generalized normal distribution. Okay. So we can see that is the expected square jump distance versus proposal scale for 4 Markov chains. Each curve represents the ESGD behavior for a different chain with a changing proposal scale. We can see at the point 1.366. So this is the value of the tau star. This value of tau is proposal scale. This gives the maximum. Okay. Now let's focus on the ESGD. This is a commonly used metric for evaluating the efficiency of an MCMC algorithm. It's defined as the expected value of the squared distance between consecutive states of the chain. This expectation of the xn t plus 1 minus xt then taking square. Here xtn and xtn t plus 1 n. This is the current and proposed state of the chain, respectively. The ESGD measures how far the Markov chain moves between consecutive steps, providing a direct way to access the exploration of the target distribution. We can see that the optimal scale tau star 1.366 gives the highest ESGD across all 4 Markov chains. So this next is the trace plot for these 4 chains. Okay, we can see that's random behavior. The trace plot for the first dimension of the 4 Markov chains using the optimal scale value tau star. These plots were generated over the total of 20,000 iterations with the initial burn-in 5,000 discarded, revealing the convergence behavior of each chain towards the target distribution. This trace plot illustrates the sampled value over time, highlighting the chain's mixing and exploration capability. Ideally, the trace exhibits a randomized pattern around target distribution, indicating effective exploration. And last, we compare the empirical CDF for each chain using the optimal value tau star against the theoretical CDF. The CDF of the generalized normal distribution is given by here. That's the CDF. Where this gamma, little gamma, is a lower incomplete gamma function. This comparison allows us to evaluate how effective the chain sample from the CDF the target. Notably, the empirical CDF for the first distribution of each Markov chain closely aligns with the theoretical one. We can see here. That's the firstly, that's the black one is the theoretical CDF, and then there is the chain 1, chain 2, chain 3, chain 4. Empirical CDF. We can see it closely match. Okay. So, and last, there are some excellent reference of the classical result in the using the diffusion approach.